Hello, good evening. My name is Jorge Sigfredo Macias Medina. I am a participant in the CMM SE 2024, and I will participate with the following talk titled Transmutation Operators Associated with a Schrodinger type operator. That being said, let us start with the presentation. So we start by introducing the mathematical model that we will be working throughout this presentation. We will be working with the following Schrodinger type equation that we have here. In this case, the delta refers to the Laplacian, the Q refers to the potential of our equation. In this case, it is a C2 function that depends on the angular component of Z. And our equation is defined over a bounded domain omega subset of the complex numbers. Our goal in this case is to construct a transmutation operator which will generate solutions for this equation. In this case, we will take a harmonic function h and we will send these harmonic functions into solutions of this equation using our transmutation operator. But first, we must define what is a transmutation operator. A transmutation operator, which we will be naming T, is an operator that must follow the following properties. Firstly, it must be an invertible linear operator defined over a vector space E. And our operator T is called a transmutation operator for two operators A and B if it satisfies the following conditions. The first of which is that T and T inverse be continuous over E. And the second condition being that our transmutation operator satisfies the following operator relationship. So for these type of problems, what we do is we establish two operators, A and B, which we wish to establish a relationship between. We construct a transmutation operator that satisfies this following property. And having done this successfully, we can construct solutions for the second operator by making use of the first operator. In our particular case, our two operators A and B will be A, the Schrodinger operator associated to our equation, and B will be the Laplacian. If we successfully construct a transmutation operator between these two operators, our transmutation operator will send harmonic functions into solutions of our Schrodinger equation. So the methodology to construct transmutation operators has been relatively well established. One option to construct said operators is to make use of either Fredholm integral operators or Volterra integral operators. In this case, the Fredholm operator was of no use to us, but we made use of the Volterra integral operator. In this case, a Volterra integral operator is an operator of the form the identity plus the following integral operator of this form, where we require of a kernel to successfully define or construct our operator. In this case, we will denote the kernel with capital H. So for these type of problems, we already know the structure that our transmutation operator must have. The difficulty relies in determining the exact kernel so that the transmutation property is satisfied. But in our particular case, we were able to successfully determine that the kernel of our transmutation operator H must be the unique solution of the following partial differential equation and satisfying the following three initial conditions. This result is summarized in the following theorem. We will define the following domain R, and we will define H to be the unique solution of said partial differential equation, satisfying the following initial conditions. Then, if these conditions are satisfied, then we have that T satisfies the following transmutation relation. In other words, T is a transmutation operator for the operators S and the Laplacian. In this case, S is our Schrodinger operator. The proof of this is relatively simple, makes use of integration by parts, makes use of the conditions that are satisfied, and we can easily verify that if these conditions hold, then T is in fact a transmutation operator for these two operators. So now that we have successfully found our transmutation operator, now we must prove that in fact the kernel of our transmutation operator exists. So for this, we will try to make use of Picard's theorem for evolutionary equations. We wish to study the following partial differential equation and prove the existence of solutions for this partial differential equation. So first, we notice that this partial differential equation can be expressed as an evolutionary equation, recalling that evolutionary equations comprise of problems written in the following form: partial T of M plus A of U equal F, where U is the unknown solution, A is an unbounded skew self-adjoint operator, and M is an analytic and bounded material law operator. So problems of this form are referred to as evolutionary equations. There are many examples of evolutionary equations, namely the heat equation, the wave equation, and the Schrodinger equation. In this case, we will try to express this partial differential equation as an evolutionary equation. And we were able to express this partial differential equation in this form. This is the same partial differential equation, but expressed in matrix form. In this case, the first matrix is the matrix operator M. The second one is A. Here we have our unknown solution U, and here we have finally our capital F. So taking the elements of our evolutionary equation in this way, we note that clearly M is an analytic bounded operator valued function, and additionally, due to the presence of gradient and divergence, we observe that A is also an unbounded operator. So finally, the final requirement we have here is that A be a skew self-adjoint operator, but this is easily verified applying properties of adjoints and using the fact that the adjoint of the gradient is minus the divergence. We can easily conclude that A is a skew self-adjoint operator. And voila, we have that our partial differential equation is in fact an evolutionary equation. So in this case, we can make use of the following theorem. This theorem is Picard's theorem. In this case, the hypotheses are those previously mentioned. Most of the hypotheses we already commented. M has to be a material law. A has to be a skew self-adjoint operator. And we have one additional hypothesis that we must verify before we are able to make use of Picard's theorem. So lastly, we will verify that our equation satisfies this bound. We take A and M as defined previously, and we consider the real part of this inner product. We use, obviously, the expression for our particular M. We use properties of inner products. We use the definition for Z, and we are able to bound this term in a way that it satisfies Picard's theorem. As a result, making use of Picard's theorem, there does exist a solution for our partial differential equation. So now that we have proven this existence and we have our transmutation operator, finally we're going to prove a few additional results. The first of which is boundedness. Various of these results will be proved for the unit ball centered at the origin. So the first result tells us that the transmutation operator T is in fact bounded. This follows from the fact that T can be expressed as the identity plus a T prime, which in this case is the integral operator part of the Volterra operator. So since it's a sum of two operators, we merely have to prove that they are both bounded. As a result, T is bounded. So we must prove that T prime is bounded. Firstly, we bound this term, making use of, firstly, the definition of T prime and making use of the Cauchy-Bunyakovsky-Schwarz inequality. Afterwards, we take the domain integral of this term. We do a bit of change of the integrals, and we are successfully able to bound the norm of T prime by a constant times the norm of H. So in this case, we conclude that T prime is in fact bounded. And since T prime is in fact bounded, we can then conclude that our transmutation operator T is also bounded. Now that we have proved boundedness, we also would like to comment over the invertibility of T, but this is a known result for Volterra operators, so our operator is additionally invertible. And finally, we would like to construct a complete family of solutions for our Schrodinger equation. For this, we will take our transmutation operator T and study its behavior applied to the polynomials zk. So we would like to calculate the image of polynomials under T. We will use the fact, of course, that H is a solution of the following partial differential equation, and making use of integration by parts, making use of Leibniz rule a couple of times, we were able to determine that the images of the polynomials under our transmutation operator are of this form. Alas, we would have desired that the formal powers would be orthogonal. In a previous work where the Schrodinger equation was studied for a radial potential, it was easily verified that the formal powers were orthogonal. Nevertheless, in the angular case, we found that they were not so. So this is the end of the presentation. This is the end of the work so far. Lastly, we have a few goals that we would like to work further ahead, namely completing the family of solutions. But this is what we have so far. Thank you very much for your attention. Have a nice day.